Hello, I'm Jonathan Lorraine, and I'm presenting our paper using bifurcations for diversity in differentiable games with my collaborators Jack Parker-Holder, Paul Vickel, Aldo Pacchiano, Luke Metz, Tal Kochman, and Jacob Forster. Finding different types of solutions has been useful in single objective minimization. For example, finding solutions that use shapes versus texture in image classification with convolutional neural networks. Differentiable games generalize single objective minimization, where we have multiple players, each trying to minimize their own loss. Solution concepts for games often involve finding points where no player can gain from changing their strategy unilaterally. For example, a Nash equilibrium. Finding solutions in games has been of increasing interest in machine learning. For example, generative adversarial networks, hyperparameter optimization, self-play, meta-learning, adversarial examples, curriculum learning, architecture search, and many others. Our goal with this work was to be able to find diverse solutions in differentiable games. For example, having players either battle or cooperate with each other might both be solutions, but we want to be able to find both of these to choose from. Ridge-Rider is a general method for finding diverse solutions in single objective minimization by starting at saddle points and branching the optimization procedure in the direction of negative eigenvalues. Also, bifurcations are areas where small changes to our parameters cause changes to our converged solution. Saddle points are a key bifurcation in conservative systems, like the one we get from following the gradient. However, following the player's gradients simultaneously in games is a non-conservative system, so we have more types of bifurcations and solutions. This is because the Hessian's generalization for games, the game Hessian, may be non-symmetric and could have complex eigenvalues. The game Hessian is shown here at the bottom, where LA is player A's loss in red and LB is player B's loss in blue. This is just a Hessian if LA equals LB, i.e. the single objective case. But, for example, in minimax games, we have LA equals negative LB, and this matrix could be skew-symmetric with purely imaginary eigenvalues. So, to generalize Ridge-Rider to games with multiple objectives, we have to find a way to deal with non-conservative system resulting from following the gradients. The game Hessian can have complex eigenvalues, and it's common to write the associated eigenvector with complex entries. However, naively following a vector with complex entries might give us complex valued weights, which we crucially want to avoid. To solve this, when an eigenvalue is complex, we look at the eigenvectors for the conjugate pair, and instead return the vector spanning the real plane the conjugate pair tells us to rotate in. Conveniently, this is the default behavior for PyTorch's eigenvector function. We also have new bifurcations besides saddles. We branch at potential hop bifurcations where the negative real part of an eigenvalue crosses the imaginary axis. There might be other bifurcations of interest too. Finally, we apply an arbitrary optimization algorithm after branching. Following the gradient is unstable for solutions with imaginary eigenvalues. So we use a method designed for learning in games like extra gradient, optimistic gradient, Lola, or whatever you want. We are interested in first finding diverse solutions in the iterated prisoner's dilemma, which is a game where players have various solutions that cooperate, like tit for tat or rim trigger, and various solutions that don't cooperate, resulting in a low reward for both players. Typical parameterizations of this game have at least 10 parameters. But this was difficult to visualize, so we constructed a new 2D problem to gain intuition into how different algorithms perform for finding diverse solutions in games. First, we constructed a problem we call the small iterated prisoner's dilemma. This is like the iterated prisoner's dilemma, except it only has 2 parameters and 2 solutions. In the top right, the players end up cooperating with a tit-for-tat strategy, while in the bottom left, players end up defecting. We show following the gradient in red, and Lola, which is a method for learning in games, in blue. Unfortunately, the simplification has only real eigenvalues, so it may be a poor proxy for more general game dynamics, which can have complex eigenvalues, like the full iterated prisoner's dilemma. Matching pennies is a 2-parameter version of rock, paper, scissors, which has imaginary eigenvalues at the solution at the center, where players behave uniformly randomly. Because the solution has imaginary eigenvalues, following the gradient diverges, while methods for learning in games converge. Unfortunately, the problem only has a single solution, so it isn't a good domain to investigate finding diverse solutions. To solve both these problems, we introduce an objective that mixes the small iterated prisoner's dilemma and matching pennies. This mixed objective has multiple solutions, complex eigenvalues, and a Hopf bifurcation separating two kinds of solutions. We applied our method game ridge rider on the toy problems. The small iterated prisoner's dilemma has a saddle bifurcation. Each branch is shown as a different color, and we have at most 4 branches here because there are 2 eigenvectors, and for each eigenvector, we can either follow it or negative it. In practice, for larger scale problems, it suffices to just branch in the eigenvectors with, say, the largest negative real part. The mixed objective has a Hopf bifurcation, so if we branch there, we can find both solutions. Notably, the solution in the center has imaginary eigenvalues, so we must apply a method like Lola after branching to find it. We also looked at finding diverse solutions in the full iterated prisoner's dilemma. Our baseline strategies for randomly initializing, then applying a learning algorithm. If we use Lola for optimization, then we found a solution where players cooperate like tit for tat every time. If we follow the gradient, then we find a solution where players defect each time. If we apply our method, which first finds a saddle, specifically the maximum entropy saddle, then branches optimization, we can find both solutions in a single run. This problem has 10 eigenvectors we could follow, but branching at the top view was sufficient to find both solutions. We also compared with branching optimization at a random initialization to see the importance of branching at a bifurcation like a saddle. This found the same solution on every branch, so it is key to branch at a bifurcation and not an arbitrary point. So, what are the takeaways from this talk? Well, first, differentiable games generalize single objective minimization, but they have non-conservative dynamics because the game Hessian can be non-symmetric with complex eigenvalues. Also, we can view methods which try to find diverse solutions in single objective minimization, i.e. ridge rider, as finding bifurcations with conservative dynamics and then branching. This viewpoint allows us to dip into the vast literature for dynamical systems and generalize ridge rider to the non-conservative dynamics in games, which are often more complicated with complex eigenvalues, new types of bifurcations, and new types of solutions. With that, I'd like to thank you for watching. Feel free to send me an email about any questions or if you'd like to chat about the project. Thanks.